So when you're looking at SN1, SN2, we want to think about the mechanism. And we're going to actually use this a lot because it's going to help us predict the product and the stereochemistry. So it's actually going to be really important for looking at what the major product is going to look like. All right, so what chemists think is there's two different mechanisms for substitution reactions. All right, and so these nucleophilic substitution, and we're going to kind of get into this here in a minute, are either going to be SN1 or SN2. And so these are the two things we're going to look at and compare and contrast and figure out which one is taking place. If we think about this, I think this SN2, so we'll go in reverse order, actually makes the most sense. So this is a process that takes place simultaneously. So one of the things you'll hear me say is the reaction is concerted, that it all happens at once. All right, so when we talk about these SN reactions, and we're getting to the mechanism on the next slide, S is going to stand for substitution, right? So our nucleophile is going to take the place of our leaving group, right? And we saw that on that previous slide, that whatever had the negative charge kicked off that leaving group, right? And our leaving group tends to be that halogen. Our nucleophile, right? So that's going to be our source of electrons. And then the last one, the 2 is going to stand for bimolecular. And then the 1's going to be unimolecular. So that number actually helps us make sense. What I would think is when it's bimolecular, when it's the two molecules are actually going to be on that substrate at the same time, right? On that compound, meaning the nucleophile and the leaving group are both having some interaction with that carbon, right? As one is coming in, it's pushing the other one out. Let's take a look at it. So this is exactly what happens, right? So if it's SN2, what you want to think about is this is going to be my nucleophile. That's my leaving group. All right, so what we have happening is my nucleophile. Remember, that is the source of electrons, and the way you're going to recognize the nucleophile is going to have lone pairs, a negative charge, something like that. So it's going to hit the carbon and push off. All right? As it's pushing these electrons in, we're starting to push this bromine up. All right, so as those electrons are pushing into the carbon, these are starting to leave. And so what happens is we represent this dotted line. So you've probably heard me say we can't ever have 5 bonds to carbon. Like Jimmy, you literally have a 5-bonded carbon drawn on this picture. Yes and no. So the dotted line means that we're starting to make a bond and we're starting to break it. So we have our bonds here, the hydrogen, hydrogen, hydrogen. But as we're forming this bond, we're breaking it. So as this becomes half a bond, this is no longer a whole bond, it's a half. As this becomes 2/3, then this becomes a third. As this becomes 3/4 of a bond, this becomes only a quarter of a bond. So these two are sharing one bond. And as this bond gets stronger, this one gets weaker. And so we're literally hitting this carbon and pushing off the leaving group. So they're happening simultaneously. And so this group is going to bump into the carbon and push this off. Now, one thing I want you to notice is we drew this group here. So it's supposed to be planar, where it's sitting like this, like my hand, flat, right? Looking right at you. The bromine was to the right. The alcohols now is to the left. So we've inverted the stereochemistry. And so we're going to talk about that on the next slide. So 2 things from this. The rate determining step has the 2 groups on at the same time. So as this group hits the carbon, it pushes off your leaving group. Right? And it's going to invert that stereochemistry. All right. The other thing about this transition state, right, if we're looking at the reaction mechanism, we've done energy diagrams before. And so remember, the bottom, the x-axis, is just the progression of the reaction, right? What we start with, what we end with. Here's our activation energy. Our transition state is what we saw up in the top one, where both of these are bound together. All right. What we want to look at is how hard is it to get over that hill, and then it's the energy exothermic. Right? The nice thing about this, and we're going to talk about this in a little bit when we see SN1, is there's no reactive intermediate. And what we're really talking about is a carbocation. And so the nice thing about SN2 is there's no rearrangement. It's just literally going to go where the leaving group is with the inverted stereochemistry. Let's look by comparison, and then we'll kind of put it all together. So by comparison, SN1 Same idea, right? The S stands for substitution, N for nucleophilic. The 1 is unimolecular, meaning that each reaction is only working at one time, meaning the leaving group is leaving, and then the nucleophile adds. On the SN2, both things were reacting at the same time. That's why I was bimolecular, because both of them were reacting at the same time. Here, it's one at a time. The leaving group leaves, then the nucleophile adds in. So each one is working at its own pace, right? One does one, and then the next one comes in. And so they're very sequential, right? One happens, then the second one happens. The other one, it all happens at the same time. The reaction is considered to be concerted, that it all happens at once. So let's see the mechanism. And so this mechanism actually has several steps to it. And so the most important step is this first one. So it gets its own slide. So what we want to see here is, here's our carbon group. It's got a bromine, right? So this is going to be my leaving group. So let me just put a little note there. So this is my leaving group. These electrons from the spawn, remember the line means 2 electrons, are getting pushed onto the bromine. And that's why I went from having 2, 4, 6 electrons to 8 all by itself. Right here it had 6 and it was sharing those last 2 to give it 8. Since these electrons both went with the bromine, that means the carbon lost those 2 electrons. So now the carbon only has 6 electrons. Remember the E with the negative is my electrons. And so it makes a carbocation. And this is that reactive intermediate, right? So it becomes trigonal planar, meaning it's flat, and it creates this carbocation. And so this carbocation is that very reactive species. And we're going to come back to this, and this is why this is going to be important. So it makes a carbocation. Now, on step 2, carbocations are really good electrophiles. And so it's a carbocation, but it's also an electrophile. Here's my nucleophile. And it's such a good electrophile, you can have it's a really good electrophile. So you can have a really bad nucleophile. So methanol isn't the best nucleophile, but it doesn't matter. Carbocations are so reactive that as long as you have some lone pair, they'll push right into that carbocation and add. Now, one thing I want to draw here is you have an empty p orbital. And so do you remember with SN2, we actually had to come exactly from that opposite face? This one, you can push in to either p orbital. And so that's why you can get 2 products. Right? So this group can add in from the right or from the left. It doesn't matter. It's going to push into that carbocation and we can get either product. And then the last step is we're actually going to see this bond as an ether. It's got this extra proton. So some other water molecule, ethanol, whatever is in solution, we'll just pick up that proton. So we grab that hydrogen, push our electrons back, and we get our product. So there's that extra step because in SN1, each thing's happening at one time, right? The electrons from the bromine are leaving and creates a carbocation, which is a really, really good electrophile. Last thing, and just what we talked about a minute ago, it can add from either side. Right? And so whatever your nucleophile is, in this case, it happens to be methanol, but your nucleophile can always add from either side. If we're looking at the reaction diagram, we're actually going to have 2 different transition states, right? Because we're going to transition from when the leaving group is leaving. So we have our carbon, and it's going to have our groups, and then that bromine is going to leave, or whatever the leaving group is. All right, and then the other one is we have our carbon, and our nucleophile is bonded. Right? In the middle, this is my carbocation. All right. And so if you notice, there's the positive charge right up on top, and the molecule sitting exactly flat. So it's making that trigonal plane. Okay. One thing that you should put into your notes, and we're going to come back to this, SN1 has no control of stereochemistry. Right? So SN1 has no control of stereochemistry. SN2 always inverts the stereochemistry. All right, so SN2 inverts the stereochemistry, meaning it switches it. So if it was wedged, it becomes dash. SN1, you have no control of stereochemistry. So let's actually look at these. So just to kind of highlight what I was just saying about the stereochemistry, for an SN1 reaction, if you have a chiral center, this is when it really matters. So if you remember, a chiral center is when you have 4 different groups, and every chiral center we can either name as R or S. So what's going to happen is, just like before, right, our leaving group is going to leave. So that means that chlorine will pop off. And so again, that's my leaving group. Okay. So it's my leaving group, so it's going to leave the molecule. It takes its electrons with it, and it makes this carbocation right in the middle. One thing that you should really highlight is it's planar and it's a carbocation. So we've lost that chirality. So achiral means it's lacking chirality, which means this group here has its lone pairs. It can either attack from the front or it can attack from the back. And the reason that it can attack from either side is because it's got that carbocation, which has that empty p orbital. Remember the one we drew on the other page, that hourglass shape? And it can lead to 2 different products. All right. So when it's an SN1 reaction, and this is true pretty much for any time you make a carbocation, if you make a carbocation, you've lost that stereochemistry and you're going to make both products. Right? So we make the S enantiomer and the R enantiomer. And so what we actually produce in this reaction is a racemic mixture. All right. So racemic mixture means we have both the R and the S, just kind of mixed together. All right. And so we're going to make it about even amount. SN2 does the exact opposite. So we're always going to flip the stereochemistry. All right, so we have our iodine is going to hit here and kick out the other one. And this one's just trying to show you that it's marking the molecule. So we have a special iodine. And so it's just going to push in and kick out. And so it's always going to invert the stereochemistry. So if we want to switch these from S to R, we just do an SN2 reaction. We push in and kick out, and we always invert the stereochemistry. And since these two are connected at the same time, it always has to attack from the backside. So we're always going to flip the stereochemistry. All right, let's try one. So really think about the stereochemistry. So this reaction is going to be SN2, and we're going to talk about how you can predict the two. Here's my bromine. That's my leaving group. And then we're going to do sodium cyanide. And usually I'll just write it as sodium cyanide. What you should think about is that sodium is going to have the positive charge. The cyanide is going to have my negative charge. All right. And you always know that because anytime you have a metal, that's the positive charge. So it means the non-metal it's attached to will have the negative charge. All right, so you know this is SN2. So the cyanide would hit the carbon from the backside and push this off. All right, so if you've got a good handle on this reaction, pause the video, draw me the major product showing the stereochemistry, and then we'll do it together. All right, let's see how everybody did. So we're going to keep the same carbon framework. Remember, this is my nucleophile. All right. And so you're always just going to flip the stereochemistry. So if the bromine is wedged, the opposite would be dashed. So we'll put our dash, we'll put our cyanide group. The sodium and bromine just go together to make sodium bromide. Right? This had a positive charge and this one had a negative. All right, so we're just going to flip that stereochemistry. All right, so we talked a little bit about carbocations before. And if you remember, if we start with a methyl, remember, a methyl would just be a carbon with just hydrogen. So if a methyl carbocation would just be all hydrogens. And then we can go to a primary, which has 1 carbon, secondary has 2 carbons, and tertiary has 3 carbons. As you go to the right, to that more substituted, you become more stable. Do people kind of remember that more substitution makes a more stable carbocation? Well, the other thing that we're going to see is if you're next to a double bond, you're going to be even more stable. All right, so we can actually have resonance stabilization. And so just like, and so I'm relating this back to things you've seen before. If you have a carboxylic acid with a negative charge, do people remember you could draw a resonance structure where you move these electrons up and down? And we could actually move that negative charge. And we actually said that made a carboxylic acid more acidic than a normal alcohol because we have that resonance stabilization. Same thing is true here. Anytime we can draw resonance, right, we're going to take this double bond and we're going to move it over. And so we can move that carbocation from one carbon to another. So on this one, it was on the right. On this one, it's on the left. Right? So I can just color code these so we can see that carbocation and a double bond moving around. So the more places you can move that positive charge, it's going to move it up one. Right? So that's what this is saying, is a primary allylic, right? So the allylic means one away from a double bond. Right? So allylic just means one away from a double bond. Benzylic means one away from a benzene ring. Right? So allylic means that a carbocation is one away from a double bond. Benzylic means you're one away from a benzene ring. All right, and both these are going to have that same stabilizing effect. What you should think is it moves it up one number. Right? So we said that methyl's the worst in terms of carbocation stability, then primary, secondary, tertiary. Tertiary is the best, but as you make something allylic, it's going to move up one. So this was a primary carbocation, but being allylic makes it behave like a secondary. Right? So you're going to just keep moving up one. All right, same thing's true if it's a secondary, right, or a tertiary, you're going to think it's one better. Right? So a secondary that's allylic would really be equivalent to a tertiary. A tertiary allylic is even better than a normal allylic. And so same idea with benzylic, right? So benzylic just means you're one away from a benzene ring. Right? So remember, our benzene ring is that 6-membered ring with the alternating double bonds. And the reason that's true is we can pull that electron density out and make that double bond and move that carbocation around the ring. So if we put this all together, this is the increasing stability of our carbocations. So the best over here, and worst on this side. All right, so as we move to the right, we get better. So we said methyl group is the worst, then a normal primary. Anything that's allylic, right, is going to be one better. So that's why you're categorizing the one allylic, one benzylic, and then the two alkyl. This alkyl is just what we've seen before, right? Just a carbocation on a normal carbon chain. And so if you kind of follow this top row, this is what we'd seen before, right? Where it's methyl, primary, secondary, tertiary. Being allylic or benzylic makes you one better. Secondary allylic and benzylic is equal to a tertiary. And then a tertiary allylic or benzylic is kind of the best, right? So those are the most stable. Right? The more stable a carbocation is, the more likely it is to happen. Right? And so that's why we kind of care about this. And let me kind of tie this together. All right, so the reason we're caring about this is we have SN1 and we have SN2. And so we want to look at these reactions and think about how can we predict which one's going to take place? Right? Is it going to be SN1 or is it going to be SN2? The way this is going to happen, right, is if it's SN1, it's going to be governed by electronics. Right? And so what you should really think about there is it's the stability of that carbocation. Right? So it's that stability of the carbocation. So the more stable that carbocation is, the more likely SN1 is to happen. SN2 is governed by sterics, which means crowding, right? The more stuff there is, the less likely it is to happen. One thing I want to highlight on here, and then we'll talk about this in more detail. X in this case is going to equal my leaving group. And generally right now it's been the halogens, but it doesn't always have to be. All right, so it's going to be my leaving group. So when you're trying to determine if it's SN1 or SN2, the very first thing you should do is find the leaving group and determine if it's on a tertiary carbon, secondary, primary, or methyl. Okay. If it's on a tertiary, it's going to favor SN1. If it's on a methyl or primary, it's going to favor SN2. The only one that really favors both is the secondary. All right, so secondary is the toughest because it favors both. All right, and so the first thing, because I'm going to ask you, would this favor SN1 or SN2? You want to look where that leaving group is. If it's on a tertiary, it's going to favor SN1. Secondary can do both. Primary can favor SN2, methyl SN2. All right, and so that's the very first place you should start. This one, you don't really need to write as much down. It's just to kind of show you that not all things are created equal. So if we're looking at this one, we want to find where this leaving group is. So it's my bromine. And we're going to look at the carbon holding it. And so this is a primary. So it favor SN2. If we look at this one, the bromine is here. It's on this carbon. It's also on a primary. So both of these are going to favor SN2. The difference is beta branching just means one away. And so here you just have a little carbon. So it's easy for my nucleophile to come in here and kick out. This one is still going to favor SN2, but now if you notice, we have all these extra carbon groups, right? Methyl, methyl, methyl around the carbon we're trying to get to. And so even though my nucleophile would still eventually be able to get in here and kick this out, it's going to kind of be blocked by these other groups. And so it's going to slow it down. So beta branching means the more stuff there is, the slower the reaction is going to happen, the harder it is for that nucleophile to get there. Just a couple more things, then we can do some practice problems. So leaving groups tend to be related to acids and bases, right? So the more stable that anion is, so remember when we talked about bases, the more stable that anion was, the better acid it was, right? It was going to more that conjugate base, whatever the anion looked like once it gave up that proton. Same thing here. Iodine is a really strong acid, right? When it's HI. Right? Hydroiodic acid, hydrobromic acid. The stronger the acid, the better the leaving group, right? So what you should think about if you're looking at the periodic table and we're looking at our halogens, fluorine, chlorine, bromine, iodine, this one's going to be the best leaving group and the worst. And there's still good leaving groups. You can still make them work. But in terms of which is the best leaving group, iodine would be there. And typically the way I ask you this is which of these would go faster, right? So the faster leaving group is going to react quicker. And so this would be the best leaving group. So these reactions would tend to go the fastest. And then as we go to the right, they go slower, slower to the point where they don't really work. All right, so iodine would be the best leaving group and it would happen fastest, then bromine, then chlorine. Here it's a water molecule. And so what's different is if we actually protonated a molecule, and I'm just going to show you up here. So let's say we had an alcohol. If this just left, right? So we drew our electrons up onto the oxygen, it would leave as hydroxide, which isn't a good leaving group. But what we'll actually talk about when we get to some reactions a little bit later in the class, we'll put a positive charge on that alcohol. And now when this kicks off, it leaves as water, right? And so that's the difference is we can actually make a water molecule on top and so it can leave as water. A carboxylic acid, remember, has a negative charge, but it has resonance, so that makes it better. And so essentially, you're just looking at your acidity rule. So if you imagine that these had a hydrogen, the stronger that acid, the better leaving group, right? If you envision it with a hydrogen, and it's because it's that same rationale that the more stable this anion is, the better the leaving group. All right. So as you go down the periodic table, you're a better leaving group. Right? And then resonance kind of helps us become more stable. And then that periodic table trends. Right? One last thing that really determines how well a reaction works, and also specifically what kind of reaction, is our solvent. Right? So a protic solvent is any solvent that has a hydrogen bond donor. And what I would kind of commit to memory is the best example of this is water. Right? So water is a really good protic solvent. So anything that has a hydrogen donated, right? So it can't be hexane because it doesn't have a hydrogen donor, right? So a hydrogen donor has to be on a polar atom. So something like an OH or an NH. Okay? If it doesn't have one of these groups, it's not going to be a protic solvent. OH, far and away the most common, but sometimes we could see an NH, right? So it's got to be a protic solvent. Aprotic solvents don't have those hydrogens, right? So they don't have anything that can be a hydrogen donor. So there's no, so it cannot be a hydrogen donor. So essentially, they don't have an OH or an NH. Almost all protic solvents are polar, right? And so the dielectric constant is just a measure of how polar those are. Aprotic solvents can be both polar solvents and non-polar. Right? And so some of the ones we'll use in this class is DMSO, DMF, and so they help determine, the type of reaction we're going to see.